Hello and welcome to this episode of Mrs. Mulvey's Math and Physics Movies. In this episode, I am going to explain how to use the buoyant force equation. I'd like you to start by reviewing the information in the notes that I provided to you. I've also copied and pasted that information below. So pause the recording, stop a moment to read through this. And then once you've read through and digested the information here, you should restart the video. The relevant equation we're going to use is this one right here that says the buoyant force, F sub B, is equal to rho, the density of the fluid that surrounds an object, times the volume of the object, times g, the acceleration due to gravity. So in this video, I'm just going to explain various ways we may use this equation. So let's look at a few examples. In my first example, I've got a block that is only partially submerged in a liquid. Mass of the block is m, volume of the block is v, and density of the liquid is rho. Now remember, when we're using our equation that says buoyant force is rho vg, this rho refers to the density of the fluid surrounding the object that it's supporting. And remember, a fluid can be a liquid like water, or it can be a gas like air because they behave in the same way. And so what I know is this. I know that that buoyant force is equal to rho, and we're told that rho is just rho. But then the volume represents the volume of the object that's actually in the fluid. And in this case, not the entire object is in the fluid, just 1/4 of it. 1/4 of that volume is in the fluid, and then I multiplied by g as well. And so the buoyant force is the rho times the 1/4 v, which we can write as v over 4, times g, making B the correct response. Let's look at another example. This time I've got two blocks that are floating at rest in a liquid, as shown, but we're given some important information. We're told that block A has a greater volume, while block B has a greater mass. And if you wonder how this can be true, just think of two substances like styrofoam and concrete. You can have a really, really large styrofoam block that has a much smaller mass than a concrete block, even though the styrofoam block might be larger. And so this one has the larger volume. This one has the larger mass. Let's also remember that we've been given one other key piece of information. And that key piece of information is that they are floating at rest. And so what that means is for each one, that upward buoyant force, because notice they're floating, so there's no normal force there. That upward buoyant force and the downward force of gravity have to be balanced for each one. So what that means is, in this case, block A has the greater volume, but the lower mass. And remember, force of gravity from gravity is mass times the acceleration due to gravity. Over here, I'm going to call this mass of A times the acceleration due to gravity. Here, the downward force of gravity is the mass of B times G. But what I know is this. This one has the larger mass. Therefore, this one has a greater downward force. And since the downward force equals the buoyant force, that upward buoyant force, that means this one also has the greater buoyant force. So basically, what I'm saying is this: because the force of gravity for B is greater than the force of gravity for A, and the buoyant force matches the force of gravity because they are at rest, then what that tells me is the buoyant force for B has to be greater than the buoyant force for A, and that makes A the correct response. Let's take a look at another one. So in this example, I've got the balloon filled with helium. It's tied to a string attached to the ground, and the balloon is floating at rest. There's keywords again, at rest. Remember, at rest means all of the forces are balanced. So what I really need to do is just look at this diagram and figure out what forces are acting here, and then I know that they're balanced and I can set up an equation. I know the total mass of the balloon. I know the volume of the balloon, right? Not that I know it, but I've been given an expression for it. I notice the average density of the balloon is rho sub B, and I know the density of the surrounding air is rho sub ATM, stands for atmosphere. So let's think about all of the forces acting on this balloon. I've got tension pulling downward on the balloon. I've got the buoyant force making the balloon move upward. There's one other force acting here, though, and that's the force of gravity. Gravity is also pulling down on this balloon. And I know all of these forces are balanced because I know the balloon is at rest. Now, if I technically wanted to write an equation, I would say this. The sum of the forces equals the buoyant force, that's upward, minus the force of gravity. I'm going to put the negative in there because it's downward, minus the force of tension, because that string's also pulling the balloon downward. I should say, keeping it from floating upward. And so I made upward positive and downward negative. And so that's the sum of the forces. Now remember, this is at rest, and at rest means the sum of the forces is 0. And so I have 0 equals the buoyant force minus the force of gravity minus the force of tension. So I want to know what tension is equal to, so I'm going to solve for tension. That's pretty easy to do. I'm just going to add F sub T onto both sides. And so I get the force of tension is equal to the buoyant force minus the force of gravity. From there, it's just a matter to find tension of filling in my buoyant force and my force of gravity. So my buoyant force, that's rho Vg. Rho, though, being it is the rho of the fluid surrounding the balloon. And in this case, it's the air, because remember, we're treating air as a fluid. And so the rho here needs to be the rho of the atmosphere. So it is rho ATM times the volume times gravity minus, and then that downward force of gravity, that's just m, mass of the balloon, times gravity. And there's our answer right there. But do be careful because, again, this buoyant force is the force of the fluid that is surrounding the object. So that means that the rho that I use is the density of the fluid surrounding the object. So that's it for this recording. As always, if you have any questions, please let me know. Bye-bye.